Hey everybody, welcome back to Physics in My Basement. Today we're going to be reviewing some ideas about torque to get you guys ready for the quest that I posted. It's going to be due on Thursday at midnight. I want to talk about torque in static equilibrium. I want to talk about torque for rotational dynamics, when a torque actually causes the change of the rotational motion of an object. And then we're going to work through a few problems. So I guess we'll get started. When it comes to torque, as you guys know, torque is the rotational analog to linear force. Let's say I have this object on a hinge, and we have a force acting on the object some distance away from the axis of rotation. As you guys know, this force, since it's away from the axis of rotation and has some perpendicular component, is going to cause this object to change its rotational motion. So for each individual torque where a linear force is acting, we can say that the torque is equal to Rf and the sine of the angle between the distance away, the R vector here, which is our distance from the hinge, and our F vector here. Keep in mind, to find this theta, you would actually have to put these tail to tail, and then you're going to see that the angle between them is theta. So it's the magnitude of R, magnitude of F, sine of theta between them. Now this one force acting on this hinge will cause this thing to rotate. So if we add up all of the torques acting, here's only one torque acting, it's going to cause this object to have an angular acceleration. So if you know the rotational inertia of the object, you can find the angular acceleration. Notice how close this is to our F equals ma. I is our rotational analog for inertia, that's our rotational inertia. Alpha is our angular acceleration. Here's linear inertia for mass and linear acceleration A. Now, what if I had a bunch of different torques acting on this object? What if I had another force acting this way? What if I had a force acting this way? What if I had a force acting down? What we can do is we add up each individual torque. And if we have an unbalanced amount of torques, we end up with some value when we add them all up, then that unbalanced torque, that net torque, will cause this thing to have an angular acceleration. If we add up all the torques and we get a value of 0, then it's not going to change the rotational motion of the object. So this is if we have a net torque, or the sum of the torques could be 0. In that case, all the torques are balanced out. It's not going to change the rotational motion of the object. Keep in mind, when we're analyzing these objects, we could analyze the rotational aspects of the object. We could also analyze the linear aspects of the object. So let's say we weren't looking at a hinge, this thing was actually free to move on its own. There could be some linear force acting on the object. So we could actually add up all the linear forces, and if there's an unbalanced force, a net force, it'll cause it to accelerate. Or if all the forces balance out, then it could be 0. So the first thing you want to ask yourself when you're looking at any kind of question is there going to be some kind of net torque on the object? And if there's an unbalanced torque, it'll cause it to change its rotational motion. It'll have an angular acceleration. You could also look at the linear forces acting in the object. And if you add them all up and you end up with a net force, that net force will cause it to accelerate. If there is no net force, then it won't cause it to accelerate. The net force will be 0 and it'll be in equilibrium. Something else I wanted to mention too, just like for linear forces, Newton's second law said that a force acting on an object could cause a change in the momentum of the object. That's actually how he defined his second law. A net force causes a change in the momentum of the object with respect to time. And the same thing with torque. If we have a torque acting on an object, it'll cause a change in angular acceleration. That's what we ended last week looking at, this new idea of angular momentum. It'll change that with time. Now, we can look at the impulse by moving things around. Delta P. So force acting for a certain period of time will change the momentum of the object. And a torque acting for a certain amount of time will change the angular momentum of the object. So this is our angular impulse, changing the angular momentum, and there's our linear impulse, changing the linear momentum of the system. Okay, so that's enough of talking about things in the abstract. We're going to apply this to our problem-solving strategy. We're going to ask if we're changing the motion, and then we're going to analyze each aspect of it to see, to solve for the quantity of interest. So let's take a look at our first question here. I wanted to review static equilibrium with torques, and I figured this was a cool question to work through. What we have is a person actually holding up a 5 kilogram object. We have a person holding up a 5 kilogram object, and we actually see that there's a bunch of different torques acting on the object. So when you have your arm here, in order to hold your arm up, your bicep actually has to exert a torque on your entire arm in order to rotate your arm. So we can look at each one of the torques acting on our arm to figure out how much our muscle is actually pulling up on our arm. I think you'll be surprised by how much force our bicep actually exerts on our whole arm here. Okay. So when we see a diagram like this, where we see like the skeletons and the muscles, we could kind of simplify the whole system by just drawing things as lines and arrows. Again, our goal is to find the force that the muscle exerts upwards on our arm. So we have, we'll call this Fm for F of the muscle. Now we also know that our ball has a force downwards because there's gravity acting on the ball. We can call this FB for ball. And now something to keep in mind too, that we have our whole arm here. The arm has mass, and if we assume that there's a uniform mass density, then the arm will have a force of gravity pulling downwards, right in the center of mass of the arm. Now, as you guys remember, for static torque, if we're just holding up our arm here, there's actually no rotation, so we can pick our reference point to be wherever we want. It's most useful to pick the reference point to be right here at the elbow, because all of the distances are already measured relative to that elbow, and I don't care that there is a downward force from the forearm here. So we could ignore that if we pick that as our reference point. All right, well, let's make some assumptions here. We're going to assume that a forearm has a mass of the forearm to be about 2 kilograms. It's a general mass of most forearms, I guess, about 2 kilograms. And for having this arm holding up this ball, we want to see what kind of force that muscle exerts upwards on our arm, what kind of torque that this creates. Okay, so looking at this system, we can see that there's no angular acceleration whatsoever because we're just holding the ball upwards. So we could already say that the sum of the torques is equal to 0. And if we're not accelerating upwards or down linearly, we could also say that the sum of the forces is equal to 0. We'll only look at the linear forces if we need to. For now, let's focus on the torques, and we'll see if we have enough information here. But if we're missing any information, we could also look at the linear forces acting on the arm. Okay. So, as you can see, we have a bunch of linear forces, and they're acting at 90-degree angles to the distance away from the joint. So we could ignore the sine of theta between the angles. So each individual torque is just going to be the distance away, r, times the force acting on the arm, which is going to be F. So we're going to look at first the muscle acting, and you want to ask yourself to figure out whether the torque is positive or negative. Does it want to rotate the arm clockwise? Clockwise or counterclockwise? Here would be counterclockwise, which will make positive. Clockwise, we're going to make negative based on our convention. So for here, we can see that the muscle is about 5 centimeters away from the joint. So we could say R muscle, given to be 5 centimeters, we'll plug that in a bit, also times F muscle. Make that positive because we would want to rotate that arm counterclockwise. Then we're going to move out to the next force, and we're going to see that the force of gravity acting on the arm wants to make it clockwise. So that's going to be negative. That's going to be RG multiplied by FG. Our labels are just to keep track of our different forces and our different distances. So we're going to call the distance away from the center of mass of the arm to be RG. And then again, we want to call this ball, that's RB for the distance away from the ball, and the ball is FB. I forgot to mention that the mass of the ball is equal to 5 kilograms. Okay. 5 kilograms is about 11 pounds, so you're holding about an 11-pound ball. And then a 2-kilogram forearm says that our forearm is about 4 to 5 pounds, which is pretty standard for a forearm. Okay, so we set up all of our torques, and we can see that the net torque acting on this system is going to be 0 because there's no angular acceleration on that arm. Okay, so let's plug in what we know and see if we can figure out the force that the bicep is exerting on our forearm. It's given in the diagram that the distance for the muscle away from the joint is about 5 centimeters, so we can plug in 0.05 meters. The force of the muscle is what we want. I'm just going to move these terms over to the other side so we can make them positive. So if we add these over, we could say that this is equal to the distance from the center of mass of the forearm, which is given to be 15 centimeters, 0.15 meters. This is so weird, teaching to nobody at all. Okay. Now, Fg, the force that's acting on the arm, is equal to the force of gravity, which is mass times the acceleration due to gravity. So we could say that it's the mass of the forearm, which is equal to 2 kilograms, multiplied by the acceleration due to gravity. If we want it as accurate of a measure as possible, let's use 9.81 here instead of 10. 9.81 meters per second squared. My setup's a little flimsy here. Okay, then we're going to add the torque from the ball here. The distance away is about 35 centimeters, which is the length of a standard forearm. 0.35 meters. And then the force that's acting at this location is the force of gravity acting on the ball. So that's the mass of the ball, which we said was 2 kilograms. No, 5 kilograms, excuse me. Multiplied by 9.81 meters per second squared. There we go. Cool. All right. And now again, this is a standard situation for someone holding up a ball. We want to see what force does our bicep actually exert when I'm holding up simply like this is about an 11-pound object. How much force is the bicep is actually creating? As you can see, we have one equation, one unknown, so we could solve for the force that the muscle exerts on the system. We didn't even have to look at the linear forces acting here because we have all the information we need for this. Plug this into your calculator, make sure you can work this out yourself. But when I work this out, I get the force that's acting on the muscle to be about 402 newtons. Now it's kind of hard to visualize what's going on with newtons, but this is about the same force that you would need to bench press right underneath the bar, about 100 pounds if you were at the gym. So the bicep exerts a lot of force. Why is it so much force? Because it's not that far from the axis of rotation of the joint. So it needs to exert a large amount of force in order to rotate that whole forearm with this mass at the end of it here. 402 newtons, your biceps are real strong. Okay, for the next part of this problem, what if we took this ball and we lowered it by an angle of 45 degrees? Now what kind of force is this bicep exerting on our system? So we're going to set this up, and as you're going to see, now we can't ignore the angles anymore because they're not perfectly perpendicular. We'll actually have to analyze this 45 degree angle. All right, gonna erase. Okay. So here's the new situation. We have this person. Oh, it took green. Okay. And we're saying that we're holding the ball down here, and there's an angle drop of 45 degrees. Okay. So now we want to look at the forces acting on each one of these locations on the arm. We still have the same distances apply all the way through. Our muscle is about 5 centimeters away from our joint, and it acts upwards. Here's our axis of rotation. Here's F muscle. And the bicep, even though we have our arm down a little bit, the bicep still has to act straight up in order to rotate our arm upwards. Halfway through, we still have our force of gravity acting on the arm. FG. And that's going to be acting, try to make that straight down as much as we can. That's going to be acting straight down towards the center of the earth. And then the force of the ball is straight down to the center of the earth. Now that we have these angles along the arm, we're going to have to use not just RF, but RF times the sine of the angle between the position vector, which is our vector that takes us away from the joint, and the force itself. All right, now even though we're lower, we still have no change in the angular motion of the object. So we could still say that the sum of the torques is equal to 0. All right, let's work through. We'll analyze each one of the torques acting on this arm to see if the force of the muscle, if it increased, decreased, or stayed the same. Okay. Now, the position vector from here, remember that we're coming from here this way. So that's what our vector looks like. And we want to find the angle between these vectors. So if I redrew it, we have our muscle vector here, but our displacement vector looks like this. So it's actually not 45 degrees between these. This is going to be sine of 135 because we have 90 plus 45, which is 135. So we have our muscle, F muscle, sine of 135 degrees. Another way you could look at this, instead of just brute force taking the sine of the angle between the vectors, you could also ask, well, what's the perpendicular component of the force that's acting at that location? And if you look at the perpendicular component, you can see that we could just take cosine of 45 degrees instead of using sine of 135. But if you plug in each on your calculator, sine of 135 and cosine of 45 ends up being the same value. Hashtag trigonometry. Okay, so we have the muscle pulling upwards. That's going to rotate it clockwise still, so that's going to be positive. We're going to subtract off the next one because it's rotating rotating clockwise. RG, FG, sine of the angle between the vectors. And if you look here, our position vector now is longer, but it's still pointing in the same angle. And the angle between these two here, which is this is your position vector and here's your force vector, the angle between them is going to be 45 degrees. That's how much we lowered our arm when we're doing when we have our ball down by 45 degrees. I gotta get used to this with nobody around, talking to an empty room. All right. So Next, we're going to say that the force of the ball is still rotating clockwise, so that's negative, RB, FB, and that's going to be sine of 45 degrees as well. And all of this is still going to be equal to 0. Because there's no net torque acting on our arm here. Okay, so let's rearrange and plug in. Remember that the distances and the forces here don't actually change because the distance is still halfway through the arm and the force of gravity acting on the arm is still m times g. Even if we have an angle there, it doesn't change the actual magnitude of the force. Same thing with the ball. So I'll let you plug in on your own, calculate it out, and surprisingly, what you're going to find when you plug everything in, that the force of the muscle is still equal to 402 newtons. And that may be surprising, but if you look here, when we change our angle, all of the angles change proportionally. So as long as you're in static equilibrium, no matter where you're holding that object, the bicep is still going to be exerting this fairly large force of 402 newtons acting on the ball. And keep in mind, this exists in real life too. If you're holding an about 11-pound ball and you have it in static equilibrium, your bicep is exerting a force of over 400 newtons on your arm in order to hold up both your arm and the ball. Okay. Any questions? You can't ask me questions. Leave me a comment, I guess. Oh, I'm ruining my setup. There we go. All right. Next. Okay. I grabbed one of your quest questions, and there we go. I grabbed one of your quest questions. You're welcome. I'm going to help you work it all out, and hopefully we can understand what's going on in this particular situation. So we have a one-piece cylinder. It has a core section protruding from the larger drum, and it's free to rotate around its central axis. That's a whole lot of words to say that basically we have this situation here. This is kind of like more of a side view of what's going on. So we have a smaller cylinder and a larger cylinder, and they're fixed together and they could rotate as one object. So we have a rope wrapped around the drum of radius 1.7 meters and exerts a force of 3.97 newtons on the cylinder. So on the outer side of the cylinder, this is the distance of 1.7 meters, and we have a force of about 4 newtons acting in the right direction. And then for the inner one, we have a radius of 0.52, and it's exerting a force of 6.5 newtons downwards. And what we want to find is the magnitude of the net torque acting on the cylinder about its rotation axis. Okay. So the fact that they're asking for our net torque acting on the system, there we go. They're asking for the net torque on the system. So if the net torque has a value, it's going to change the rotational motion of this object. We'll have an angular acceleration. If there is no net torque, it'll be 0 and we won't be changing the angular acceleration. But that goes beyond what we're looking for. We just want to find the number, the magnitude of the net force, net torque acting on the cylinder about its rotation axis. All right, so our net torque is going to be the sum of each individual torque acting on our drum here. So we could call this top one torque 1, and then this inner one torque 2. Torque 1 plus torque 2. And when we set up our equations, remember that clockwise is going to be negative, counterclockwise is going to be positive. So torque 1 is our upper torque here. So for each individual torque acting on the object, we take the distance away from the axis of rotation, the magnitude of the force, and the angle between the position vector and the force vector. And as you can see, if we drew our position vector from the axis of rotation straight up to this force, this is acting at a 90-degree angle. So we could ignore the sine theta there because sine of 90 degrees is just 1. So for our first torque, we're going to say R1, F1, and we're going to make this torque negative. Keep in mind that clockwise, that idea of a clockwise torque being negative is just our convention. If you specify that you want to make clockwise positive, you're free to do that. But I would highly recommend that you just keep clockwise being negative, counterclockwise being positive, so there's no confusion. You will get the right answer if you change it up though. So the first torque is negative R1 times F1, and then the next torque is going to be plus R2 F2. That one's positive because this torque is going to want to rotate that object counterclockwise. Okay. Now, we know our rate, the distances away from the forces. We know the forces themselves. We can simply plug in and calculate the net torque acting on this object. The net torque is equal to negative. R1 is given to be 1.07 meters. F1 is given to be 3.97 newtons. Plus R2 is 0.52 meters multiplied by 6.49 newtons. Remember, this is negative. Now, if you plug this all into your calculator with these numbers, you should get a net torque to be 0.8731. And don't forget our units for torque. Newtons times meters is Newton meters. Okay. Now, you always want to think of what does this number mean? What does that tell us about this cylinder and how it's going to rotate? This positive value for torque, that tells us that if the cylinder is going to rotate, it's going to change its rotation counterclockwise. There's going to be an angular acceleration on the cylinder counterclockwise with these two forces acting on it. You might be asking, well, this is less force than this is acting. How could this be beating the 6.5 Newton force to rotate it counterclockwise? Remember that torque not only depends on the magnitude of the force, but the distance away from the rotation axis. Because this is further away, this force exerts a greater torque on the cylinder than this force does. If they gave us the rotational inertia of the cylinder, then we can use that information if we know the rotational inertia of the system, we know the net torque, we could find exactly how much the cylinder, how much angular acceleration the cylinder is going to have in the clockwise direction. Okay. Good. Next question. All right, this is the last question I want to work out with you guys. Here, we have a situation where we have a disc. We kind of have this pulley with a rope wrapped around it. And we hang a mass on the end of the rope, and then we let the mass go. They tell us how much the mass accelerates downwards. They tell us the radius of this pulley, and we want to find the moment of inertia of this disc, of this pulley system here based on the given information. All right, so there's a lot of information here. We want to organize it all. We have this pulley with some mass big M, some radius little r. I'm going to use letters here just to keep track of everything, but keep in mind that the radius of the pulley is given, the mass of the pulley is given, acceleration is given, and the mass of the box is given. Okay, and we want to find the moment of inertia of this pulley system. Okay. this little m. And we know it's going to have a downward acceleration of a, which is given. And our goal is to find the moment of inertia of the disk. Like we talked about in class, we can't assume our pulleys are massless or frictionless anymore. We have to use the information to analyze these more true-to-life situations. Okay, when it comes to these types of problems, we're going to look at the net torque acting on our disk here, and we're going to look at the net force acting on this box. This is a coupled system, so they're going to work together to create the motion that's described in the problem. So we're going to look at the net torque of the disk, and we're going to look at the net force on the box. Using these two together, we should be able to find the moment of inertia of the disk itself. Let's break this down and we'll see what we know and what we can find. So when we let this box go, there's really only one linear force acting on this disk, which is going to change the rotational motion of the disk. The very fact that this is accelerating downwards tells us that this is going to be spinning at a faster and faster rate. So the sum of the torques is equal to I alpha, because there is a net torque acting on the system. And this is great because now we could see that our I popped up, and we could use this to find the rotational inertia of the disk itself. Our goal is to find that capital I. And if we look at this little box here, we know that there is a net force acting on the box, and it's equal to the mass of the box times the acceleration of the box. Okay, let's hold off on this. Let's see if we have enough information to solve for that capital I of the disk. And if we don't, then we can look at our linear forces acting on the box. All right. So for the disk, we have one linear force acting on the disk, and that is the force that the rope is pulling downwards here. And that force is some distance away, which is the radius of the disk, and the force is acting downwards. So we could see that the force and the position away from the axis of rotation make a 90-degree angle. We could ignore sine theta once again. So for the one torque acting, we could say that it's R, the little r, which is the radius of the disk, that was given, times the force that's pulling downwards. Well, what force is pulling downwards? Your first guess might be the acceleration due to gravity of the box, but keep in mind that that's not the direct force that's pulling downwards on the disk. The force that's pulling down on the disk is actually the tension force of the rope. And we can't assume that the tension force in the rope is the same as the force of gravity of the box, because this whole system is accelerated. We can't set them equal to each other. So R times capital T, which is tension in the rope, that's what we're defining here, is equal to I alpha. So we know that tension is acting up, Fg is acting down. Should have drew my free body diagram earlier. Sorry. Okay. Now, we don't know tension in the rope, and we don't know angular acceleration, but we do know that there is an expression for angular acceleration that relates this linear acceleration to the actual rotational motion of the disk. We know that the tangential acceleration A is equal to R alpha. Now, when we're looking at the disk, yes, we're looking at the tangential acceleration of this point on the edge of the disk, but the acceleration at this point of the disk has to be the same as the acceleration of the box, or else the system wouldn't be coupled together. It wouldn't be accelerating at the same rate. So this A is actually the same as the linear acceleration of this point on the edge of the disk. Good. All right. So we could find an expression here for alpha. Say that alpha is equal to A over R. Now we could say that RT is equal to I times A over R. All right. but here's our last problem. Our goal is to find this capital I. We still don't know t. T wasn't given in the problem. So we're gonna have to figure out a way to get an expression for t so we could solve for that rotational inertia of the disk. Here's where we look at our linear forces that are acting on the box. We're gonna see if there's some connection. Well, we know there's gonna be a connection between the tension of the rope here and the linear forces acting on the box. Okay, so let's take a look at our box. We see that there's two forces acting on the box. We have tension acting up and gravity acting down. What we're gonna do is we're gonna call this way positive. That way we don't have to plug in any negative values for our acceleration. Okay. So we have, if downward's positive, then we could say that Fg is positive minus T is equal to little m times A. Okay. And again, I'm calling down positive. That way I just don't have to plug in negative for the acceleration. If we called up positive, then all you had to do was say that it's tension minus the force of gravity is equal to m times negative A. You'll get the same answer. I'm just trying to be clever with our sign convention here. All right, let's keep working through. So Fg of the box is going to be equal to little mg minus T is equal to little ma. This is looking promising because we know the mass of the box, we know the acceleration due to gravity, and we know the acceleration of the system. Let's solve for T. T, moving this over and back, should be equal to mg minus ma. That's our tension in the rope. We need this expression to plug it in here so we could find the angular, rotational inertia of the disk itself. Let's take this expression, plug it in. We get R multiplied by T, which is mg minus ma equals I times A over R. Okay, at this point, we're pretty much done. All we have to do is rearrange to solve for capital I here. So rearranging, let's see, we multiply both sides by R, divide by A. We can say that the rotational inertia, I, is equal to R squared. M, pulling out this little m, then it's going to be equal to g minus a all over a, and that's our expression for the rotational inertia of the disk. Notice that all these things are given: the radius of the disk, the mass of the box, this is little m, g, a, and over a as well. Okay. Plugging that all in, I got a rotational inertia of about 2.57 times 10 to the minus 2. And remember, our units for rotational inertia is kilogram meters squared. Check your work, make sure you can get to the same answer that I'm getting to. And guys, keep in mind that when you're following through, just like in class, when you're following through what I'm doing up here on the whiteboard, make sure that each step makes sense to you on your paper. And if there's any questions whatsoever on any of the steps here in each one of these problems, post it on the discussion board. We'll try to work everything out together. All right, and that's it. This was our review on torque and statics and rotational dynamics. Tomorrow I want to post more videos with conservation of angular momentum, doing some angular collisions, and we'll go from there. Thanks for sticking with me, guys, and I'll see you soon.